friends, I am here to give you a demonstration of rotational symmetry from standard 7.
A shape has rotational symmetry when it still looks the same after a rotation. Let us discuss about figures which may or may not have rotational symmetry. This is the shape of a crescent moon. The center of this shape lies somewhere here. When I rotate this shape about this point, the crescent moon has to rotate through 360 degrees to match itself for the first round. This shape matches itself exactly once when we rotate it. Hence, this shape does not have rotational symmetry. Next, look at this shape. This is the shape of an arrow. It has its center somewhere here. Now, keeping this point fixed, if I rotate this arrow around its center, it will match itself only once after one full rotation. Hence, an arrow does not have rotational symmetry. Let me give you another example of a figure that does not have rotational symmetry. Look at this quadrilateral. More accurately, I would tell this is a trapezium. Let me mark the vertices of this trapezium as A, B, C and D. Okay. Let me write here also, that is on the figure. This particular figure has its center somewhere here in the middle. Let us rotate it and check. We continue rotating it until and unless each matches itself. We see that it fits exactly onto itself only once. Hence, a trapezium does not have rotational symmetry. Now let us discuss about some shapes that have rotational symmetry. Look at this square. I am placing it here and marking the vertices on a paper. The square has its center here, that is at a point where the diagonals intersect one another. If we join the vertex A with the vertex C, we will obtain one of the diagonals. If we join the vertex B with the vertex D, we will obtain the other diagonal. Now both these diagonals will intersect at a point here. Now keeping this point fixed, if I rotate this square, see what happens. Let me draw its boundaries. Now when I rotate it through 90 degrees, the boundaries will coincide. That is, the figure will match itself once. After the second rotation, the figure again matches itself. Now we go for the third rotation. The figure again matches itself for the third time. Go for the fourth rotation. We see that the figure matches itself for the fourth time. The vertices have come back to its original position and will not rotate it further. So, this figure has rotational symmetry of order 4. Let me tell you that the order of rotational symmetry is the number of positions during a full turn where the shape looks the same. The angle between positions is always 360 degree divided by the order of symmetry. Now look at this figure. It is a parallelogram. The point of intersection of the diagonals lie here. Let me write down the vertices on the paper. Now keeping this point fixed, I'll rotate the figure around this point. When I rotate it through 180 degrees, I find that the figure matches itself once. In place of D, we have B. In place of A, we have C. In place of D, we have B. And in place of C, we have A. Right? This shape fits onto itself after a rotation of exactly 180 degree, a half turn. Let us rotate once again. We see that the vertices have come back to the original position. Hence, the rotational symmetry of a parallelogram is of order 2. Please remember, a figure with rotational symmetry of order 2 is said to have point symmetry. Now, look at another figure. This is a regular hexagon. It has 6 vertices A, B, C, D, E, F. Its center will be somewhere here. When you join the opposite vertices, you will obtain the point of intersection of the diagonals at this point. Let me just roughly draw the boundaries of the regular hexagon on a paper. And mark the vertices as A, B, C, D, E and F. Right. Now see what happens when I rotate. I have just rotated once through 60 degrees and A has coincide with the vertex F, and also the 6 sides coincide. Second rotation matches itself. Now third rotation also matches itself. Fourth rotation matches. Fifth rotation matches. And finally, sixth rotation also matches. The vertices have come back to their original position. Hence, a regular hexagon has rotational symmetry of order 6. Similarly, in case of an equilateral triangle, the centroid of the triangle will be the center of the figure. The centroid is defined as the point of intersection of the medians of the triangle. It will lie somewhere here. Let me mark the vertices on the paper as ABC. If I rotate it through 120 degrees, the figure matches itself for the first time. Similarly, second rotation matches, and finally the third rotation also matches. The vertices have come back to their original position. Thus, an equilateral triangle has rotational symmetry of order 3. Next, look at this figure. You can very well identify that this is the center of this figure. When we rotate it, it will match itself 4 times. Hence, it has rotational symmetry of order 4. Look at this one now. I am writing down the vertices. Its center is here. If we rotate it once, the figure matches itself. Second rotation done, and the figure matches itself again. Third rotation matches. Fourth rotation matches. Hence, this figure has rotational symmetry of order 4. Look at this figure. It is the figure of 4 quadrants joined together. This is the center. Keeping this point fixed, if we rotate it through 90 degrees, the figure matches itself once. Second rotation also, the figure will match. The third rotation, figure matches. Fourth rotation also matches. The points have come back to their original position. Hence, this figure has rotational symmetry of order 4. I hope the concept of rotational symmetry is clear to you.
I shall come again with a new chapter of mathematics from the 7th standard. Till then, stay safe, take care, good day.